And good afternoon, Four Sigmas. Alex here. Today we're going to be doing the photoelectric effect lab with Pasco equipment. So we got our mercury lamp and all of our equipment already set up. If you need instructions on how to set it up, the Pasco video actually does a really great job, and your professor will provide it for you. So you're going to let the lamp warm up for 10 minutes first, and it should be noted, as you can see in our data here, we're going to start at low wavelengths and high frequency. So as we go to lower frequencies, we need less stopping voltage because the electrons are going to be directed toward an anode, and as that anode gets more positive, you need less stopping voltage. So my lab partner Tony here has already set up at our first wavelength of 365 nanometers, and so we're going to record the stopping voltage, which is negative 1.910. So now we're going to switch to the next wavelength, higher wavelength, lower frequency, and he's going to change the voltage. This voltage is becoming more positive until we get a current of 0. And it should be noted that this lab actually pretty much put the nail in the coffin for classical physics. The only way that scientists could explain this effect was Einstein's postulates, and that's actually what he got his Nobel Prize for. So we're tuned now, and our stopping voltage is now negative 1.437. Now we're going to switch to the third, again higher wavelength, 435.8. Again a lower frequency, so we should have a less negative, more positive stopping voltage. And it takes a light touch, but we've got minus 1.225 volts. Now we're going to change to the next one. 546.1 nanometer wavelength. And as you adjust it more, the changes actually get dramatically more sensitive, so slow and steady does it. And our stopping voltage is minus 0.692. And our final wavelength of 577 nanometers. And this experiment can be run using the 850 interface. We're doing a manual data entry because we actually don't have a couple of the cords we need, but it's good to do it the old-fashioned way as well. So now we have minus 0.572 volts. So now what we do is we have all of our data. We can go over to our graph here and apply a linear fit to our data points. So as you can see, I'm going to drag this out so you guys can see it. We have our slope as negative 3.67 times 10 to the minus 15. Now, we can calculate Planck's constant using that slope. So we're going to go over to our calculator, and I've already pre-populated these values inside here. So I'm going to put in my slope as negative, and I'll actually do a positive value because we're using the absolute stopping voltage. So 3.67, and Pasco does scientific notation like this: E minus 15. So now we can check that our experimental value of crap. And as you can see, we've applied a linear fit to our data now. Our slope is negative 3.67 times 10 to the minus 15. But we're actually just going to use the absolute value of that over in our calculations. So we're going to go over to our calculator, and I've already pre-populated all of the calculations we need. So our Planck's constant, because our slope equals Planck's constant over the charge of an electron, we're going to take our slope times the electron charge to get our experimental Planck's constant. So you see I've already put that in here, and we get 5.88 times 10 to the minus 34. And what I'm actually going to do is, there we go. There's our slope. There's our experimental value of Planck's constant, and our error is just going to be standard error calculation, Planck's constant minus our experimental over the accepted value times 100, and we get about 11.26% error. Not bad. So that's how you set up to do experimentally finding Planck's constant. If you are doing the next section for light intensity, we'll have a different video covering that. Thanks for watching, and hope you had a great experiment. Hope your numbers come out as good as ours did. And we'll see you next time.